All right, so our next speaker is Andrew Marks at UCLA. And he's talking about Borel Matchings and equidecomposition.
All right. Well, thanks very much to the organizers for the invitation to talk. So I want to talk about a couple of theorems in this sort of general study in descriptive set theory of when some sort of definable combinatorial problem has a definable solution. And so I want to present one positive theorem and a negative theorem about when we can find a definable solution to some matching problems, and talk about some applications that these theorems have. So I'll start by recalling some basic notions. So a graph G on some vertex set X is bipartite if we can partition the vertex set X into two pieces I'll call them A and B, so that every edge in the graph is between the point of A and a point of B. And so pictorially, we have these two sets, A and B, and all the edges lie between them. And since I'm studying matching problems, many matching problems naturally will occur on a bipartite graph, and that's the case that I want to deal with. So a perfect matching now of a bipartite graph is simply an injection from A to B using edges that come from the graph G. So.
Injection or bijection?
Bijection. I guess an injection would be a one-directional matching. And those are of some interest as well. So a perfect matching of G is a bijection from A to B using edges from G. All right, and so there's this very classical theorem of Hall which characterizes infinite bipartite graphs when we have a matching. If G is a finite bipartite graph, with bipartition AB, G has a perfect matching if and only if for every finite set F of vertices,
it's fine. Everything is fine.
Everything's finite. But I'm about to generalize to locally finite graphs using a compactness argument, and F will remain finite, but the graph will become locally finite. So for every finite subset F of A or B, the set of neighbors of F is at least as large as F. So clearly this is a necessary condition if we're to have a bijection. Hall's theorem is that it's sufficient. And a compactness argument, as I said, generalizes the theorem to locally finite graphs. So here, by a locally finite graph, I mean that every vertex has finitely many neighbors. Okay. So Arnie Miller actually asked in his problem list from several years now ago whether there's some Borel analog of Hall's theorem. So in particular, if we ask for this graph G to be nicely Borel, and we're working in this infinite case now, where we have some infinite locally finite graph, supposing your Borel graph satisfied Hall's condition, is there going to be a Borel matching, for example? And there's nothing particularly special about Borel there. We could ask for a definable analog for other notions of definability. And that's interesting as well. And the answer is no. So in fact, the first example in the literature is due to Laskovich, and it's a very simple graph that gives a counterexample to the definable version of the statement. There is a Borel bipartite graph, in fact, where each vertex has exactly two neighbors. And the graph does not admit Borel matching. All right, so what's the idea behind Laskovich's example? A two-regular graph okay, where I'm going to draw things now where I'm thinking of this maybe as the set B, and this is the set A, does not have very many matchings. This is very overdetermined situations where as soon as you pick one edge to be in the matching, that decides absolutely everything else. And so if you say this point is matched to this point under your matching, all the edges in the graph have to be directed towards the right this way. And if you match this way, all the edges would have to be directed towards the left. And so what Laskovich did is he just found a nice example of a nicely definable two-regular graph where, for example, if in some small open set comeagerly you've made this choice as to which direction you go on the line, you can go a long distance away, and that choice you've committed to in that giant open set of vertices will have committed you to going the opposite direction, somewhere far away, which is a contradiction. All right. So just exploiting the fact that deciding one edge in the matching decides all of them, it's easy to find examples where you can't find a Borel matching of a Borel graph. The first theorem that I want to discuss, because for a long time we didn't really know any other counterexamples that weren't based in some simple sense off this one, is I want to talk about some counterexamples to Arnie's question that have to do with graphs that are irregular of higher degree.
What do you mean by Borel? So how is this based?
Okay, so to be precise, a Borel graph, let's say, is a graph, since we're doing descriptive set theory, whose vertex set is a Polish space. So, and always it's not going to be interesting unless it's an uncountable Polish space. So a graph on the reals and whose edge relation is Borel. Okay.
How Borel is this example?
Well, abstractly, by uniformization, if you have a Borel graph and every point has two neighbors, it's generated by two functions. And you can change topology to make these functions homeomorphisms or continuous. So a priori, all Borel graphs have to be very simple in Borel complexity. Their complexity has nothing to do with how hard it is to color them in the Borel hierarchy.
It's very simple. You're very geometric.
Yes, that's right. And in fact, I can even tell you Laskovich's example, which the one he originally gave was extremely geometric. The graph, the two sets A and B are each copies of the unit interval. And what you do is you pick some irrational number alpha. And if you think of this as the first copy of the interval and this the second copy of the interval, I can draw the graph now in the plane. And each point here should be related to 2 points in the other interval. And starting at alpha, you draw a line with slope 1 and a line with slope -1, and you finish off this kind of box here. And this example has the required property that if in some tiny open set here, you decide I'm going to match to points on the lower line generically, then you will have quite far apart in the graph points pointing in either direction, which is the contradiction that you're after. Right? Just because of the geometry here induced by alpha being irrational. Okay. So what I want to talk about, though, is the following theorem, giving basically a different way that's not based on this very rigid structure that occurs in the two regular case of getting countersamples. So you might hope, and it's not such a crazy hope, that this was in some sense the only obstruction. We know many phenomena in descriptive set theory where this sort of ergodicity, where you have some two regular graph, is the only thing preventing you from definably carrying out some combinatorial construction. Some examples are, say, coloring graphs. If you don't have a two regular graph, you can always, and it has degree D everywhere, you can color it with D colors. Mod a null set if it doesn't contain any cliques, for example. Or n selection, if you have a graph and it doesn't have two ends, then modulo null set, you can find a one-ended subforest everywhere. These two regular examples are a typical source of pathology, and we'd like to know if often they are the only source of pathology in some combinatorial context, and here for matchings they are not. So here's the theorem. For every d greater than or equal to 2, there is a bipartite Borel graph where every vertex has degree D, and the graph admits no Borel perfect matching. Great. So I want to sketch a proof of this result. No, I mean, even when D is 3, this was unknown until...
I know, I understand, but what I say...
Sure, I might as well say cyclic. Find somewhere to fit that in. Okay. Good. So the examples that I'm going to show you are also quite easy to define and natural. They come from certain group actions. The way that you prove this theorem is with a pretty direct application of Borel determinacy. Okay. And so I want to sketch what the graphs are and then what games you use to show that there can't be a matching. So let's begin with the groups. So let gamma, and I'm going to just sketch a proof for the case d equals 3. That has all the interesting ideas. Let gamma be the group with 2 generators, and I'll call them A and B. And so that A cubed is the identity, and B cubed is the identity. Okay, so this is really the free product of 2 copies of Z mod 3Z. And I'll just draw quickly because the geometry of this group is the key to this construction. I'll draw a picture of the Cayley graph of the group here. So there are these 2 generators, A and B, whose third power is the identity. And so if this is the identity in the group, I can start, and I have A and A again, and then I'm back to the identity if I keep following A. And similarly, I can follow B, and then I'm back to the identity. And now starting at each of these points, instead of using the A generator, which keeps to 1, I could use the B generator. Okay, and over here, I have A again. And so the Cayley graph here just looks like a bunch of triangles glued together, where each triangle corresponds to either the generator A or B. Okay. My graph is going to live on the space of functions from that group to omega. And in fact, the group acts on that space of labelings. So think about labeling each group element here with a natural number. If I forget what the identity is, and I just remember what edges correspond to A and B, if I can pick any other point and declare that to be the identity in the group, and I have another copy of the Cayley graph. And that's how the action works. It works by shifting this point which I declare the identity and keeping the same labels everywhere on the graph. So I'll define algebraically that action. So gamma acts on the space of functions from gamma to the omega by shift. Okay. And where for x and omega to the gamma and group elements gamma delta and gamma, if I want to act by gamma on x, and this is another function from gamma to the omega, so I need to define what it does at each group element. This is equal to x of gamma inverse times delta. All right, but for me, it's always easier just to think about this picture. You've labeled with natural numbers, and this shift just corresponds to shifting around where you start the labeling, where the identity is in that picture. All right, and I need one more definition. Let f of omega to the gamma be the free part of the action. Okay, so if I have a trivial element of gamma to the omega, it may be that when I shift by group element, I get the same point again. Right? If I label everywhere by 0, then shifting doesn't move me anywhere. And I want to discard that trivial part of the space. The free part is equal to the set of x and omega to the gamma, such that for all non-identity group elements, gamma dot x is not equal to x.
Not equal.
Thank you. All right. So I'm almost ready to define the graph that I want to consider for this theorem. the graph is a bipartite graph, and I'm going to tell you next what the bipartition is. And that involves two very simple equivalence relations. So
I thought you were giving us a tripartite graph. No,
no.
bipartite. I'm sorry.
So let EAI be the equivalence relation on this space where x is EA equivalent to y if a to the n dot x equals y for some n. Okay. So these equivalence classes on this space all have size 3. Right? Pictorially, they look like sort of triangles on each orbit. Because we're in the free part of the action, the orbits individually just look like this group acting freely on some set. There are these little triangles, EA classes, and EB similarly. Okay, so here's my bar partition. Let A be the set of EA classes. Okay, and let B be the set of EB classes. And the graph I'm interested in is the intersection graph on that set. So let G be the intersection graph on A union B. So that is, if I have R and A and S and B are adjacent, if their intersection is on empty. Okay. And in particular, if you look at this picture, an EA class is this 3-element set. An EB class is this.
Intersect S.
Thank you. Yeah, R intersect S. So these are two 3-element sets. Because the action is free, they correspond to two triangles, one coming from A, one coming from B, and if they intersect at a unique point. Okay, and so edges here, edges between R and S, or between elements of A and B here, really correspond to points in this space, f of omega to the gamma. So their intersection will be a singleton. Okay, so edges in G correspond to elements of the free part of omega to the gamma. Okay. So if I have two of these triangles here, an A triangle and a B triangle, and they intersect at a unique point. And the graph kind of looks like this Cayley graph quotiented by the relation of being the same triangle. And so if I were to draw a picture now, this is what G looks like. It's just a tree. Okay, each triangle corresponds to a point in G. The intersection graph is a 3 regular acyclic graph. All right. So I claim the graph has no Borel matching. It's perfect. And the proof, as I said, is with a game.
A and B, of course, are standard Borel spaces, right?
Yeah, so you can identify A and B with, I don't know, subsets of f of omega to the gamma to the 3, right? The 3-element sets in this space. Yeah, so this is definitely a standard Borel space. This is a Borel graph. I mean, or if you prefer, instead of taking this space, you could take the real product to the 3 and then quotient by an appropriate equivalence relation, which is smooth. Great. So now here's the game. So let's make a game for building elements, or rather an element, x, in the free part of this action. Okay? So I'm going to make a game that just makes an integer labeling of this Cayley graph. Okay? And so the idea is that player 1 will define x on reduced words beginning with powers of a. Player 2 defines x on words beginning with powers of b. And at the end, I haven't told you exactly in what order they define the value of x on these group elements. It's unimportant to understanding the larger structure of the proof, but at the end, the winning condition is that, let's say player 1 wins if the x that I make doesn't correspond to an edge in the matching. So I'm setting up a proof by contradiction where I assume that there's a Borel matching that's perfect of the graph. This then becomes a Borel winning condition. And by Borel determinacy, there's a winning strategy for one of the two players. I want to find now some point in the graph which is either unmatched or some point which got matched to more than one thing. So it's not giving me a bijection. Either it missed something or it mapped two things to the same point. All right, so the situation here is going to be pretty symmetric. Let's suppose one wins and get a contradiction. So pictorially, once again, here's my Cayley graph. Here's a and a squared, and b squared, ab squared, etc. Pictorially, if this is the identity, player 1 decides what happens over here, right? Words beginning with powers of a. And player 2 decides what happens over here. Yeah.
So in the picture of the tree, do perfect matchings correspond to maximal independent sets?
No. It's easy to find maximal independent sets that don't correspond to matchings. Because you can easily, match this up here, match this here, and then there's no place to match this guy. Yeah.
I mean, is there something nice they correspond to in that picture?
Matchings?
Yeah.
They correspond to
I mean, without
themselves.
just decoding what matching means.
I suppose the dual problem, if you remove the matching, what remains is a forest of lines.
Okay.
But that's the only thing that I know. Okay. So suppose 1 wins. I mean, what you should think of is that if we allow the strategy of 1 to act here on words beginning with powers of A, no matter what we do here for player 2, and we can control what happens there, this point corresponds to an unmatched edge. Okay? So if we allow the strategy to act to define a labeling here, we can do whatever we want on words beginning with powers of B. This point will correspond to an unmatched edge. And what I want to do now is combine several strategies for player 1 to make a point in the graph which is completely unmatched. Right now, just playing one copy of the game, I can make sure this edge isn't what it's matched with. But I can also make copies of the strategy that I play other places in this Cayley graph to correspond to make sure that all of its possible edges it could use to match aren't in the matching. That's the idea. Right, and somehow the structure of the group lets me simultaneously play different strategies at the same time. So this is the freest possible group based on these having these 2 sorts of triangles in it. So the idea is combine strategies to make an unmatched point. All right. So once again, the picture is this is the generator A. If I let player 1 act here, this corresponds to an unmatched edge. But if I copy that strategy and shift it and let it act here, this point will correspond to an unmatched edge. And if I copy the strategy and let it act here, this point will correspond to an unmatched edge of this triangle. And so this triangle is unmatched to anything. Okay? So combine strategies to make an unmatched point x so that algebraically x, b dot x, and b squared dot x are all winning outcomes of one strategy. Okay. And so the remaining details to fill in are that I can simultaneously use in making x, b dot x, and b squared dot x, the strategy for player 1 to make all these 3 things simultaneously, and that those strategies cohere enough in the way that the game is defined to make a well-defined x, so that x, b dot x, and b squared dot x are all winning outcomes of the game. Okay, and that corresponds now to an unmatched EB class. Okay. And the reason it works is geometrically in the picture. If I take the set of words beginning with A, b dot that set and b squared dot that set are disjoint. And so the set of group elements that player 1 wants to define in doing this are all disjoint sets, and so there's no conflict between what the strategies want to do. Okay, and the rest is just clean up, making sure I get a copy in the free part of the space and making sure that all the rules of the game work out. What happens if player 2 wins? That makes a matched point. But then shifting the group elements beginning with B by A and A squared, I can make a point that's matched to several things. And that also gives a contradiction. So that's the end of what I wanted to sketch here. So we have this interesting situation now. I guess the title of the workshop is The Role of the Higher Infinite in Mathematics. There's this very simple looking theorem, which I've erased now, which says that there are Borel graphs that are deregular, that don't have Borel matchings. The only proof that we know is from Borel determinacy. And it would be fascinating to know if that's required. In fact, the same sort of idea with games on Cayley graphs proves several other combinatorial results in this framework of descriptive graph combinatorics. For all of these different results, it's unknown whether those theorems require Borel determinacy. We certainly don't have any other proofs. So I want to end with a short coda. This was this first result, this impossibility of defining definable matchings in definable graphs. I want to end quickly with a positive theorem. It's a little more recent. And it has a different application. I suppose it's worth mentioning that this problem for me about Borel matchings came up in computability theory when I was trying to prove something about the complexity of the recursive isomorphism relation in the hierarchy of countable Borel equivalence relations. And these techniques I used to show something about how you couldn't do a reasonably nice reduction of something there to something else. But Borel matching problems have turned out to have several different relationships to seemingly somewhat different looking problems. And what I want to end with it is a nice other application along those lines, this time to problems in equidecomposition. All right, so here's this positive result about matchings. Suppose G is a locally finite Borel graph with bipartition A and B, and so that there is an epsilon greater than 0 such that for every finite subset F of A or B, the set of neighbors of F is at least as large as 1 plus epsilon times the size of F. Okay. So that's the assumption. This is some barely strengthened form of Hall's condition, where I add an extra epsilon of neighbors everywhere. Epsilon can be as small as you like.
Are you assuming any regularity about A and B, or are they Borel, or are they just arbitrary?
No, A and B can be arbitrary here. Yeah. This condition is really about finite sets that are all consisting of points of even distance from each other. So you can define this locally without actually referring globally to some bipartition A and B.
Yeah, actually, I always forget why do you split it into A or B like that? It's because later on you have a technical condition where it has to split into A and B.
Yeah. All right, so let's finish the theorem. Suppose I have this extra epsilon of room in Hall's condition. Then generically I can find a Borel perfect matching. So there is a comeager set C so that G restricted to C has, and C can be chosen to be Borel, has a Borel perfect matching. So abstractly, this first theorem that I gave definitely has this sort of expansion. So even if you strengthen Hall's condition as much as you like, you could put 10 million here for all I care. You can, in general, find a Borel perfect matching. You may hope, though, that after you throw away a small set, you can. Okay, and this is an example of a theorem like that. After I'm willing to discard a meager set, I can find a Borel perfect matching of what remains. So this is certainly ruling out some sort of bare category approach to proving the same theorem that I just gave, at least for these particular graphs, which generically will have perfect matching. But this had another nice application, which is the original reason that Spencer and I proved it. And that requires me to talk a little bit about paradoxical decomposition. So suppose A is an action of a group gamma on some space X. We say the action is paradoxical if I can partition X into finitely many pieces and of two types. So I'll say A1 up through AN, and then B1 up through BM. Okay, so altogether this is a partition of X. So I can partition X into finitely many pieces, and I can find finitely many group elements. And I'll call them gamma 1 up through n and delta 1 up through n. So that both gamma 1 A1 up through gamma n AN partitions X. And delta 1 B1 up through delta M BM partitions X. Okay. And so, for example, the Banach-Tarski paradox. So here, in the Banach-Tarski paradox, the action that you're using is the action of rotations on the ball in R3 minus the origin. Okay? And the Banach-Tarski paradox says that I can partition that ball in R3 into finitely many pieces so that I can then take some of those pieces and, after rearranging them by rotations, recover a copy of the ball. And the pieces that I left over, I can also rotate to obtain a copy of the unit ball. I mean, typically this is stated also using translations, and then the balls end up being disjoint, but this is what's really going on here. Okay, and then as far as the origin goes, there's some trick to get rid of that problem. All right, so it had been some open question for a while what sort of regularity properties the pieces in the Banach-Tarski paradox could possess. Right, obviously the pieces here cannot be Lebesgue measurable, because 1 is not equal to 2. On the other hand, could the pieces have the Baire property, for example? And this was some question from 1930 of Marczewski, which was solved quite a long time later by Doherty and Foreman. So the question of Marczewski was, can the pieces in Banach-Tarski have the Baire property? And the answer is yes. And this is Doherty and Foreman. Sometime around the mid-90s. Okay, but Spencer and I were re-looking over this old result, And now that there's some small industry of sort of descriptive graph combinatorics, wondering whether we could reinterpret it and understand it in a little more of a refined way. This construction that Doherty and Foreman do is very tied to the geometry of the Banach-Tarski paradox. It's some rather long construction. We're able to use this to prove a more general result. Which also has the benefit of being a very simple argument. Which perhaps I can sketch for you in its entirety. Here's the theorem. So suppose a group gamma acts on a Polish space X by Borel automorphisms. So what I'm about to do, of course, the action needs to be in some sense definable to have any hope of proving a theorem like this. If the action has a paradoxical decomposition, it has one where the pieces have the bare property. Okay. So for free in general, if you have any nicely definable paradoxical action just for free, you get such a paradoxical decomposition with bare measurable pieces. The proof is just converting the situation of paradoxicality into an appropriate matching problem, massaging it a little bit, and then applying this theorem. And this theorem gives bare measurable matchings, which then will correspond to bare measurable paradoxical decompositions. So here's the proof idea. Suppose S a subset of gamma.
Anyway, are you assuming that the group is Polish group or anything?
I had no assumption whatsoever about the group.
Well, it would be completely abstract group.
Yeah, but actually, you might as well only do this for finitely generated groups. And the reason is paradoxicality only talks about finitely many group elements. So if an action is paradoxical, it's because the restriction of that action to some finitely generated subgroup is paradoxical. Yeah, and so it's not so impressive to know that the group is arbitrary. Suppose S a subset of gamma is finite. I associate now to the action a particular graph where matchings correspond to paradoxical decomposition. Okay, so suppose S is finite and symmetric. Let the graph determined by the action, that finite set, be the graph on 3 copies of X where IX is adjacent in the graph to JY if there is a group element in the set so that gamma dot x equals y and exactly one of I and j is 0. So the picture is I take this space on which my group is acting and I make 3 copies of it, essentially corresponding to the original space and then the 2 copies that I want to create by this paradoxical decomposition. So I have 0 cross x, and then I have 1 cross x and 2 cross x. And then I make edges between the 0th copy of x and the other 2 copies of x, precisely when some group element from my finite set takes me from a point here to a point here, or a point here to a point here. And it shouldn't be surprising that a perfect matching here corresponds to decomposing x into 2 copies of itself using these finitely many group elements, and hence corresponds exactly to a paradoxical decomposition. So this graph has a perfect matching if and only if A is paradoxical using group elements from S.
Sorry, what's little a?
A is the action. Sorry. I should have said that at the beginning. Yeah, let A be the action. So here's how the proof of this theorem goes. Suppose you have a paradoxical action. That means you can find one of these graphs with the perfect matching. Abstractly, that just means that graph satisfies Hall's condition, okay, and not the strengthened version that I need. But because of the particular geometry of the situation, if you change S to its square, you gain this extra epsilon of room just by an easy finite counting argument. So the action's paradoxical. You can find this graph, which satisfies Hall's condition. Amplifying S to S squared makes it satisfy the stronger version of Hall. Now we can apply this theorem, get a bare measurable matching, which corresponds to a bare measurable paradoxical decomposition. And that's the proof. And this is not such a hard theorem on itself to prove either.
But what about that co-meagre set?
Yeah. What you do is you use choice to fill in the matching off the co-meagre set. And that's no problem. So that you get a perfect matching defined everywhere, but since it's Borel on a co-meagre set, the pieces that it induces will have the bare property. We're just, I think, beginning to see the amount that sort of definable matching problems are useful in studying various sorts of problems in descriptive set theory. I'll mention one nice open problem. Is Lebesgue measured the unique finitely additive rotation invariant measure defined on the n-sphere, or the Borel subsets of the n-sphere? So is Lebesgue measure the unique finitely additive rotation invariant measure defined on Borel subsets of the n-sphere? That has a positive answer in dimensions 2 and above. This is some famous theorem of Margulis, Drinfeld, and Sullivan, if you define the measure on the Lebesgue measurable sets instead of the Borel sets. But it seems to be begging the question to find it on the Lebesgue measurable sets if you want to show Lebesgue's the unique nice rotation invariant measure. Because of their theorem, the Margulis, Drinfeld, Sullivan theorem, if you ask about Borel sets, it corresponds exactly to some effective matching problem, where you want to effectively do paradoxical decompositions in the sphere of Borel null sets. And Spencer and my approach here seems useful. Unfortunately, so does some unproven theorems of Peter Sarnak about Diophantine approximation in the rotation group on the sphere. Anyway, I'll stop there. Thanks very much.
But you're not able to get a stronger theorem than the conclusion that the pieces have the bare property because of, is that where the co-meagreness plays a role here? That is, it's actually a Borel perfect matching, so you're dealing with Borel sets, but only on a co-meagre set. And it's when you fill in, when you try to extend it, that's where, because the co-meagre, so that's where the bare property comes from. Is that right?
That's right. Of course, you can't get a Borel perfect matching of these graphs in general, because that would give you Borel pieces in the paradoxical decomposition. If you apply this for example, to the action corresponding to the Banach-Tarski paradox, then you'd have Lebesgue measurable pieces achieving the Banach-Tarski paradox, which is a contradiction. In general, you cannot possibly hope for any Borel perfect matching to find everywhere if there's some Borel measure that the action preserves, probability measure. So in some sense, you need some largeness notion where sufficiently random conal slits are considered small to have this sort of theorem.
Oh, so what if there was no invariant measure? What if you had a finitely generated group and the reduced equivalence relation was compressible?
It's a fantastic question. Questions like this are related to, say, working on a null subset of the sphere and trying to prove the open question that I just asked. And so they remain open. I'm very interested right now in situations where you can find Borel matchings because of the many applications that they seem to have. Vulnerability of actions is another example. Tarski's circle squaring problem is another example. And abstractly, you could hope for Borel matchings in these sorts of situations. We don't know yet how to construct them.
I have one question about the previous theorem where you constructed your base space was F free part on omega to the gamma.
Yeah.
So presumably using two colors will be.
Yeah, it's fine to use 2 to the gamma. My proof doesn't work so well in that situation, but you can apply afterwards this theorem of Robin Tucker-Drob and Brandon Seward that say there's an equivariant map from omega to the gamma to 2 to the gamma. And so while omega is more convenient for the proof, the same graph on 2 to the gamma has the same property that there's no Borel perfect matching.
So the theorem of Hall, could you kind of make the epsilon depend on the f? So kind of.
Okay, that's an excellent question. If epsilon depends on f in some reasonable way, it would be nice to hope that this happens still, that you have generically perfect matching. Our construction doesn't work if epsilon decays as f grows in any way that's kind of non-trivial. However, other people have proved generically of perfect matchings in this situation where epsilon does decay as f grows. There's a recent theorem of Grabowski, Mathe, and Pikuko who show that if you have the circle and the square of the same area in R squared, after discarding a meager set, you can find the Borel equidecomposition of those two sets. And what they do is precisely that, where the Hall's condition that you get in the associated graph has some extra neighbors for everyone, but the amount is roughly the size of the perimeter of f. In R squared and in Z squared, because Z squared is an amenable group, that decays as the size grows. But still, in fact, using our exact same algorithm for making the matching here, they are able to prove that generically perfect matching exists. So I don't know any general sort of hypotheses where you can weaken this. I would love to know them, but there are particular examples where it does work, just based on a very careful analysis of the geometry.
More questions? Just thank Andrew again.